the word simple here, because we're not the first people to give a combinatorial interpretation here. So earlier, but more complex interpretations were given by two sets of authors that I know of. One is Ira Gessel and Gerald Viano in their seminal paper about applying Lindström's lemma and determinants. So they weren't able to give an interpretation of these guys in terms of non-intersecting lattice paths, which is what this paper was about. And in fact, but again, they were aware that the interpretation they were giving was more complicated than they would like it to be, because they in fact ask in the paper, is there a simpler way to get a nice combinatorial interpretation of this? So in some sense, this whole talk is an answer to their question. Yes, there is. And another more recent paper by Art Benjamin and his student Sean Plott gave a very complicated, although maybe more, arguably more elementary, but really involved way to interpret these things. So those exist, but ours, I think...
Even more complicated than Gessel, you know?
Yes, in some ways.
Oh, but they claim it's more elementary?
It was, Art Benjamin's thing is tilings, and this was a tiling interpretation.
Ah,
we're
so
also going to use tilings.
If you like tilings.
If you like tilings, you like that one better, right? And we're actually also going to use tilings, but in a much simpler way than Art did. And I can definitely make this statement that these were more complex, both because of both I've given talks now, both where Ira and Art have been in the audience, and they both agreed with me. So this is not just my own opinion. Okay, so as I just mentioned, we're going to be using tilings. So let me show you, and that should come as no surprise for people who are familiar with Fibonacci numbers, because tilings often come up in that setting. So let me tell you what you need to know about tilings in order to understand the rest of this talk. Not very much. So let's let script T of n be the set of tilings of a row of n boxes by disjoint monominoes and dominoes. So by that, I mean I've got monominoes, which cover one box. I've got dominoes, which cover two boxes. And I want to cover all of my boxes, and I don't want any overlaps. They're disjoint. So again, an example is worth 1,000 definitions. What does T3 look like? Well, I've got three boxes, right? I wanted to, well, one obvious way to do it is to just put monominoes everywhere. But I could also use one monomino and a domino. How many ways are there to do that? Yes, I'm just checking to make sure people are following. There's two ways, right? You can either put the domino first, followed by the monomino, or put them in the opposite order. Okay, good enough. Let's not just look at these objects and count them. Let's look at what they are with certain weights. So we're going to weight a tiling. So T is what I'm going to use as a canonical tiling in kind of the very most obvious way. It's going to be S to the number of monominos, T to the number of dominoes. Okay. Now let's see what happens if I take the weight generating function over here. So let's sum over all the things in script T3 that are weights. The weight of this is S cubed, right? Because I got three monominos, and each of these guys has weight ST, and there's two of them. Have we seen that polynomial fairly recently? Yes, it's that one. And that is not, as I like to say, an accident. So this is brackets 4. notice there's a shift in subscript that you're going to have to keep track of. This is for tilings of 3 boxes, we get the 4th polynomial here.
So it's more natural to redefine it?
No, it's more. This is more natural for us because of this definition. Yes, there are 2 ways to define the Fibonacci numbers depending upon your initial conditions. But if you want your factorials to work out, you are forced with this and therefore have to live with the shift. I will tell you a way to get around the shift later. And everybody see that that should be true. And let's prove that because it's easy. The other thing I want to show to emphasize the fact that this simple, I'm going to show you every single step in the proof. So, you know, how many talks do that? You will see everything. I will hide nothing. So the lemma is, of course, that if I sum over all the tilings in Tn, their weights, I get the n plus first thing. And I love these proofs because they're one-picture proofs. Because think about it. These guys are defined by a recursion and initial conditions. So how do I prove these are equal? I need to show that the sum side satisfies the same initial conditions and recursion. I think you can do the initial conditions on your own. Okay, and it's the initial conditions which show you why you have to do the shift. So we only really need to worry about the recursion. That's the only place where there's any meat. So to show the sum has the same recursion as brackets n plus 1, again, just draw a picture. What does this set of tilings look like? Well, it can be broken into 2 subsets, right? The tilings that look like this, by which I mean the tilings that start with a monomino. If I do that, how many things do I have left that I need to tile? Minus 1, I think, yes. Together with disjoint union, what are the only other types of tilings they can have? Those that start with a domino, right? We only got 2 types of tiles, in which case the rest of them, there's n minus 2. And now we're done. Think about it. It says that the generating function for this is, well, the generating function for a single monomino would be what? S, right? S is the weight for monomials, times the generating function for the n minus 1 guys. We should be looking at this while we're comparing, right? This is giving you the monomino. This is giving you how to tile the rest of them. The next ones start with a domino. Dominoes are weighted by T. And then the rest. End of story. Everybody happy? No problems? Good. I'll get that. And the proof. Okay. Now, using this, you can prove all sorts of nice things about Fibonacci numbers, or more generally their weighted cousins, in very pretty combinatorial ways. So let me give you, as a corollary, something that we will actually need, which is a formula for what you get if you take curly brackets m plus n. This looks like this. M times n plus 1 plus t times m minus 1. How do you get that? Again, the proof is simplicity. So you're going to use the lemma, of course. So this side is counting ways of tiling this guy, and I can break this guy into 2 subsets as well in the following way. So let's label the squares from left to right, 1, 2, up through m plus n minus 1 for the last square. And now let's look at what happens between the m minus first square and the mth square. Okay. Well, there's 2 things that could happen. Either there's a domino there. If there's a domino there, then the rest that I have to tile here is how much? How many squares do we have down here? M minus 2, right? And then from m m plus 1 onto this is going to be